So let us wait for some time, like 1-2 minutes at 3:05. Like we shall like start. Is it fine with everyone? Am I audible now?
Yes, sir,
Yes,
you are
yes,
audible, sir.
Okay. So the recordings will be uploaded on the YouTube channel, and the link of that will be shared to you by the NPTEL people, and I'll be sharing both the recording as well as the presentation and whatever we shall be doing here. So some people are still joining. Yeah, let us take 1-2 minutes. So there shouldn't be anything that will get skipped. So my screen is visible to everyone.
Yes, sir.
Okay. So if anybody is not able to like hear, or like my sometime my screen is not able to share, kindly let me know. So I think like it's 3:05. So we should get start. We should start, and people like will subsequently be joining here. And there is someone who wants to join. I'm not able. Why is not he able to? Why is not he able to join? I think if anybody like is not able to join, kindly let me know or text me anything. So let us get started with today's problem solving session. So good afternoon everyone. My name is Adnan Farooq Khan, and I am currently pursuing PhD from IIT Delhi. So this is our first problem solving session uh, for the course Design of Power Electronic Converters, which is being taught by Professor Shabrinath from IIT Guwahati. This is the first of the problem session, and this problem solving session will continue for 8 weeks, and In this problem solving session, what we will incorporate in this, what I'll incorporate in this is like whatever has been taught during this week. I'll just give a brief preview, like so that I'm able to refresh like whatever has been taught in this week, and then we shall move to the problem solving session. Like these problems are not like the current problem which have been giving to you, but these problems will be somewhat related to, somewhat similar to what is your assignment. So that this will help you in like solving the assignment. And if you are having any confusion, like you can ask the questions, and you can just type the questions in the chat, and I shall be here to remove your doubts or anything about this. So coming to the course, so firstly, like I told you, I'll be briefly going through the summary, like what had been taught in this week. In this week, like first, what was being like taught by the professor is like the basic applications of the power electronics. What are the different fields, like what are the different applications of the power electronics? As you know, like in the current current times, like power electronics is everywhere, wherever you see, like be it motor control, be it your computers, like chargers, everything and everywhere you will found the power electronics. Like this is like now an essential part of our lives. And after that, like there were the two topologies that were discussed during this week, and one was this buck converter, and another was like the H bridge, or you can see a full bridge, full full bridge. Sorry, I actually I'm not feeling well today, like pardon for anything. So there was like a buck converter was being taught, like how mainly this course will be about the design of things. There is an idea, like about, like you have read about what is a buck converter, what are the different operations, how like buck converter operates, what are like different equations. But I will briefly also go through this, and this course will delve into only the like how we choose different components, how can we can choose different components of our converters, and like their steady state analysis, and we are able to design these converters for different power ratings. And same goes with the H bridge. So coming to the like the first, what different applications, what are the different applications of the power electronics in the current scenarios? Like I told you, like this power electronics is like in the every field. If you will find it everywhere. It is like a diverse like its application is very diverse. It can be found like a first of the applications where it is found is the motor drives. Like we have DC voltage source, and we wanted to drive a motor, we want to control the motor. And we have an inverter where we'll be converting that DC to first AC, and from that AC, like we will run our motors. Not only that, like we will run our motors, like there are other aspects, like how to control the motors, how we will like do the speed control, and other things. Like there are a number of things that are under this like motor drives, and all of this is done by our like there are different converters, different modulation strategies that we will be doing, different control methods, how we do the control of this motor drives. Like this plays an essential part in the motor drives, like how to drive these motors and everything. And other things, like you have seen like switch mode power supplies. You will have seen like your chargers. We have a AC, like then we'll generate a DC from that. We have a inverter, we have a DC, like we have a let us say a DC voltage of some amplitude, and we want a different amplitude at the output, be it a buck operation. That means like the output voltage will be less than the input, or sometimes we want a boosting operation. That means like we have an input that is lower than the output. And like there will be a different converter topologies, where we'll be using different topologies in different different applications, like your adapters, like you'll see different topologies what are being used there. Other other application is like you have our servers in data centers, we have our inverters at our homes, and UPS that are being used, UPS for like these computers, uh, like inverters. Sometimes like when our light goes off, we have a battery that stores our energy, like how it converts from DC to AC, like at our homes, like everyone in today's time will have an inverter. And behind everything there is a power electronics involved. From one thing, how we are able to generate the other thing, how we are able to generate AC from a DC. There's some power electronics involved in it. In the subsequent lectures, you'll see different topologies, like what are the different topologies for the inverter, what is the topology, what are different modulations for this, like if we have a DC-DC conversion, what are the different topologies that we may have, like if we have a non-isolated one, what are the different topologies that can be there, and if we have an isolated one, what are the different topologies that can, like in this DC-DC we have a buck boost type of a thing, like in the isolated for lower power ratings, like we have a flyback for. So someone has asked like what is the last date for the exam registration. I think like you can go to the NPTEL page of this, and there you will find the info regarding the registering for the exams and courses, like certified courses. Like I'm not sure like what are the dates, but you can visit like to this course and you can find your data there, and you can apply accordingly. And one of the current, like which is a like, maybe it is, but I'm not quite sure, like you please visit the page of this course and you can look at there, like I don't know if it is 11 March or not. So like we don't actually deal with it, actually like there is an NPTEL people, they deal with all these registrations and all. So other applications like which are like of quite interest right now, like is the renewables. Like there is a lot of research going on in the renewables, like PV and wind, where in the PV we are able to generate from this solar, is we are able to generate the DC voltage, but we want to integrate, like feed its power to the grid, and we're able to have this AC, convert this DC to AC. So there also like we have this power electronics involved. Power electronics is involved in every aspect, like in wind we have a different in wind also like we have a variable power, because like the wind won't be constant at every time, like there will be a variation in the flow of the wind. Sometimes the wind will be very high, or sometimes low, and there will be a different power levels that we generated. How we manage that thing, how we are able to transfer from one level to other, like there is a power electronics involved everywhere. Like you will subsequently see different topologies that are involved. Other application is like electric wheels. Like you see there is a boom of electric vehicles, everyone is talking about the electric vehicles. In the electric vehicles there are different things. One is the drivetrain that is on the vehicle itself, like we have a batteries, we charge these batteries through chargers, and from this DC we generate the AC, and we have some motors on our on wheels, like they are driven by these AC voltages. Like we can have different motors, be it induction, big synchronous motor, or any other like a different uh, people use, like different companies use different motors, like you can see into that. But the idea here is like we have a DC source, from that we want to generate the AC. So we have there like different topologies of AC. We can use a three-phase VSI or some other topologies, maybe some of the companies will use some other topologies. Idea here is like here as well, the power electronics is involved everywhere. And other aspect of the electric wheel are the chargers. Now we have these batteries now that after flying the vehicles for a lot of time, like now our battery is drained, now we want to charge our battery, now we want our charge our batteries, like we go to the charging stations, and these are very high power level chargers, not that phone chargers which are of like very low power levels. We have like a fast chargers in there, like everyone might have seen like a Tesla charger, how this at seen. The idea behind that thing is the power electronics involved. Like we have a AC, from that we charge a DC. How we charge that, different topologies will come into the picture. And other thing is like currently like research is going on is wireless power transfer. The wireless power transfer you will have seen in the phones mobile phones right now, like the iPhone or Samsung. Currently like they provide this wireless charging. So how that is being done, there is a power electronics involved behind that. How that is done, I don't know if that will be covered in this course, but you can see like the power electronics is involved behind that. Now that is on the lower level. Now if you want to like charge our cars wirelessly, we can there as well. We have different converters which are being used to charge our vehicle wirelessly. Like there is not a physical connection between a charger and a vehicle, but still we are able to charge this. Like there we have an inductive charging, or we can have a capacitive charging. Like that is beyond the scope of this what I say, like this course. But you can get an idea like how diverse is this power electronics. Like you can see in there is no aspect, if you can see no aspect is there where power electronics is not in our lives. Be it like our vacuum cleaners, we convert it, how it is run, how that there is some like motor inside, that is a motor, how that is like controlled, it's working, everything. Like some power electronics is involved behind that. And this was about like applications, just the gist and the idea, about the applications of the power electronics. Now coming to the like there are like two topologies that have been taught in this, like I told you, buck converter and this, just a minute, buck converter and edge bridge, that have been taught in this week. And before moving to that, like how we are able to like would I design that, like analysis of these converters. Before that, like there were some assumptions and like that were taken into the consideration for the analysis of these converters. So first of the analysis, first like assumption that was taken was like we'll be talking about these converters in the steady state, not the transient state. Like in the steady state, like when our voltage and current levels are at our steady state levels, like you can have initial starting transition where our voltage builds up from 0 to a certain output voltage. After that we have some steady state voltage, and at that steady state what we have, like this inductor. And you might have seen, like as I already told you, there is some idea, like a notion, like you have read the basic about, because like this is a higher level course, like about the design, going into the design aspect only. So there is notion like about the basic of this, like inductor volt second balance and capacitor charge balance. So we know that at a steady state, like we have this for the inductor, we apply like this inductor volt second balance. That means like the energy that is stored in energy that is stored in one interval, same energy is like transferred in the other interval, so that like volt second is balanced. That average voltage across this inductor will remain as 0 in one switching cycle. So as you can see, if this inductor volt second is not balanced, what will happen, like during this like a startup, we have, if the inductor volt second is not balanced, like as our voltage will rise to some point, but it will not dip to the same point. So what will happen in the next instant, like our voltage will increase, and this will continuously happen until we'll reach some steady state point where we have like the rise in one interval will be the fall in the other interval, so that the average of the voltage across the inductor is zero. That is taken into consideration, and that happens in the steady state. So we will take into the picture only in the steady state. We won't be discussing about the transient analysis, like what will happen at the starting and all, and that will you will see in other courses, because like that is beyond the scope of this course. And similar for that, like for inductor we have this volt second balance, like the average of the inductor voltage in one switching cycle should be zero. And similar for capacitor, we apply the charge balance. That means the charge stored in one interval is equal to the other interval, so that the average current so the average current through the capacitor is zero. So this is the first approximation that is taken into the consideration. And there is other approximation that is taken into the consideration, is the small ripple approximation. So here we take into the picture like the ripple that we know, like if we have some voltage with some ripple, we have some current. It has high frequency component and average component. The high frequency component will flow through the capacitor, and the average component through the load. So what we want is the ripple across the capacitors to take very low, so that there is not much variation in the output voltages. Because like in some applications there is like these are sensitive loads, like which cannot withstand a variation in the loads, like in the data centers and their data centers, there shouldn't be much of this variation in the output voltage. So the ripple across the capacitor is taken very small. And same with the inductor, but compared to the capacitor, like we take some ripple, like 10%, 15%, 20% sometime of the output current as the ripple. And you'll see how we'll be discussing in our problem, as well as during the analysis of this buck converter. And also like the other assumption that is taken is the circuits are taken to be ideal, like whatever the components that will be in their circuit, like switches, diodes, like inductor, capacitor, what we assume is they are ideal, like there is not some non-ideality associated with it. If we consider these non-idealities, like then we have to incorporate those as well, and that analysis will be quite different from this. And that's also like beyond the scope of this course. And mainly like this course is confined to the steady state analysis, how we design different converters in the steady state. So coming to the first converter that was being taught in this course is like a buck converter. Everyone knows like this is the circuit of the buck converter, where we have a like input. Like everyone knows like buck converter. What it does is like we have some input voltage V in, and at the output we have some output. What it does is it does the buck operation. Buck operation is like at the output we'll be getting the voltage that will be lower than the input voltage. And you might have like read about this buck converter, so I'll go through it, like the analysis part of it, like how we come to these equations. So this is the circuitry of this buck converter, where we have an input, then we have a switch here, like a MOSFET is being drawn here, and in here we have a diode that is connected in an anti-parallel function. Like the anode of this is converted to the neutral point or ground, you can say, and the cathode is connected to this point. And then we have an inductor, and then we have a capacitor, and then we have some load. So there are different voltages that will be given here. Like since we deal with the designing, like we want to know what are the different voltages that will be across these switches, current that this switch will carry, what will be the voltage across this inductor, capacitor, and across the diode, and so on and so forth. Here you can see these things, like I out is the average of the, like here IL current will have the average component as well as the switching component. Like the average component will flow through the load, and this the switching component will flow through the capacitor, that is IC. That IL will be equal to, if we apply the nodal here that IL will be equal to IC plus I out. Similar with other things, like we will go in the different intervals, like in the D in 1 minus D interval, and we'll see. So how this buck converter work is like, we have a buck converter here, now we shall like look into the buck converter in first DTS interval. What is this DTS interval? So for certain amount of time, like we are switching this, turning on this switch. When this switch is turned on, like we'll get this positive voltage across the here diode and the negative here. That means like our diode will be reverse biased, so this diode won't conduct and we'll be having a circuit in this fashion. Well, we'll be having an input, then we'll be having as the output, and there is like an inductor that is connected between the input and the output. This we will be having an IN, and this will be an IS and IL. So we know, like as I had already discussed, like we will be analyzing this circuit in a steady state, and as I told you, like this average voltage across this in a switching cycle will be equal to 0. So we'll see what is the voltage across the inductor in this DTS interval. DTS is in whatever, like let us say we have some switching frequency of Fs, and the time interval corresponding to that will be Ts, that will be equal to 1 by Fs. So for that portion, like how we do it, like we turn on our device for some fraction of that, switching interval, and usually our D varies from 0 to 1. So if it is 0, that means the switch is constantly continuously off, and it is 1, that means it's continuously on. And if we vary from 0 to 1, that means for some percent of time of the switching interval, our switch will be turned on, and for some interval it will be turned off. I hope you get this point. So we'll be writing, like I told you, like we'll be dealing with this volt second balance and charge balance across this capacitor, like voltage across the inductor. We'll see like the VL that is given here, and we know voltage across the inductor is given by L di by dt. So we have not given that current through the inductor is IL. So VL will be called L dIL by dt, and if we see what is the voltage that is being impressed on this inductor, it is like V in minus V out, and this voltage will be positive because like we know V in is higher than the V out, because this is a buck converter. Like our output is lower than this input. So we have in the DTS interval V in minus V out across this inductor, and simultaneously we will see what is the current that is through, because we have to do the charge balance to this capacitor. We know that the charge is conserved for this, it is 0 across, like we do for this. Like like I told you, we have, if we apply the Kirchhoff's law here, we have like the current entering the node will be like, if we take positive and current leaving as negative, like we will get IL will be equal to IC plus I out, or we can write IC will be equal to IL minus I out. So we know that IC will be equal to C dV by dt, and that will be equal to IL minus I out. So we got the two equations for the voltage and the current, yep, for this DTS interval. Now we will look into like what are the different voltages that will be impressed across different components. Since like we have turned on this switch, like this switch is conducting, like we know that and we are assuming that this is ideal, we know that this voltage across this switch will be equal to 0. So that is V switch is 0, and we know like if we apply the Kirchhoff's voltage law here in this loop, so you can see the voltage that is being VD has to block is V in this. So this diode should be rated for this V input voltage here. Like if you can see, like this has to block this V input voltage. So V diode in this interval will be equal to V in. So similarly, if we see what is the current that is through this device, like that, this switch, if you can see the input current, like I switch current, is same as that of IL. So you know, like the current that this switch will carry is the inductor current, which will have a average component as well as the switching component that we will see in the subsequent slide. And since like this voltage is like this diode is reverse biased, and like there is no current that will flow through this diode, and as such this ID will be equal to 0. This was about like the DTS interval. Now this was the interval for which we had turned on our switch and turned off our diode. Now coming to the this sorry, just a minute. Coming to the 1 minus DTS interval. So here you can see in this DTS interval, so what now we do, now we will turn off this switch. Now when this switch is turned off, so you can see the circuitry will be like this. Now this diode will conduct, and this switches is turned on. You can see our input current is 0 because like this switch is turned off. And what will be the voltage that will be across this VL? And you can see, if you can see, like positive will be equal to like this minus, and positive will be here. That will be like minus V out will be impressed across this inductor. So during 1 minus DTS, the voltage across the inductor will, we know VL is called LDI dt, that will be equal to minus V out in this. And now if we can see, this is the voltage that we see here for the 1 minus DTS interval across the inductor. Now for the capacitor, now we have to see what is the current that is flowing through the capacitor here. Since if you can see, like IL will be flow through here, and it will like split into like I out and IC. Similar to this, IC will be equal to IL minus I out. So this was about the current and the voltages. Now if you see, now we will see the what are the different voltages that will be blocked by different components. Like coming to the no, like we have taken some convention here, like inductor current. Let us say some current was flowing in here in the inductor. So what will inductor do? Inductor won't allow any change in the current. So it will like see the current should flow in the same direction. And we have some now see just a minute that I'm telling. And we have some convention, and like initially we cannot change the polarity here. Let us say we have assumed like positive here and negative here, that we also see here. Like we have to follow the same convention, that what will happen, and we will see what are the voltage with respect to that convention. And with respect to that convention, if this is positive, like you can see the minus V out will be implemented across this. Hope like you got this. So how diode I'll let you know. So there is like this current that is flowing just a minute, that is what I am saying now. So this is the convention that I am saying. Like this is the convention that is there. Like we'll keep positive here, but we know like there is to be some path that needs this current to flow. Like this is going to this current will flow in the same direction in the IC and I out. And what this current will that we will come V out is less than V in. I am subsequently, like, don't jump to the questions, as like I'll see in the subsequent slides how it comes to be less than V out will come into. For the time being, you just see like V out is less than V input. So this this current will cause like this diode to conduct, and it will conduct this diode. What? So you just wait, like I am going so I am just a minute, like I am going. What happens is actually like this polarity will reverse, and what you are seeing, like this polarity will reverse and this will get forward biased. This is for the like the what I am saying is the convention. Like if we have kept here plus minus here, we will see with respect to the convention. what happens. And we know like the polarity will change here, that will cause this current will flow in this direction, and that is called the forward biasing of this diode, and that is there. But with respect to the conventional, if we are following V out, that is V out will be equal to VL. But when we have taken certain conventional, we have to see with respect to that convention. So you just wait, like in the next slide, like it will be clear to you. So you just wait this slide, like let me complete this first, and then you have then if you have any confusion, like that I'll clear. So here VL and IC will be this. Now we just show this, the V switch is turned off, then the voltage, if we apply like this voltage loop in this, that it will be equal to like the voltage that which is to be blocked by this switch is V in voltage here. And since diode is conducting it, so V diode will be equal to 0. And since like our switch is not conducting, like I switch will be equal to 0, and you can see here the source current, that is from the source I in, like it will be discontinuous. It was conducting for like a certain interval, and now it is turned off for certain interval. So, and I diode will be here, it will be equal to IL, like we know like this current will flow through here, and here both of them will add, like this will be equal to IL, that will flow through the diode here. So now we know like we have to apply like volt second balance and charge balance for this capacitive current and voltage across this inductor. So if you take two intervals, in DTS interval we have V in minus V out for the DTS time, and for the 1 minus DTS we have minus V out. Like if we and that should be equal to 0, because like average in the switching cycle, because what I was telling you about it should be 0. When we equate to the 0 and solve that, you will see that V out will be equal to dV in. And here you can see V out depends upon D and V in, and we know that D varies from 0 to 1. And since it is a fraction, that means this output voltage will always be lower than the input voltage. Got clear here? Like who was asking why this is, like if you go through the lectures note and like the transcript, you'll see when this is solved, and this will come out to be like V out will be equal to dV in. And similar case for the IC should be equal to 0, and we have like IL minus I out for in DTS interval, and for other as well, like from this will we get IL when we equate that thing, you will be getting this equation. I haven't shown the complete derivation here back because that has already been taught. This is just an overview and if you go through the lectures and the transcript that are being provided to you by the NPTEL people, there it is being like derived in detail. And if you have any question, like go through them. If you have any questions as well, like in the next problem solving session, you can like ask me like what has been done here, and I'll clear those things. But go those two things we have to like apply this volt second balance and charge balance to the capacitor current, and we'll come out with this equations. So now we'll see about how these like waveforms are there. Just now this will be clearer here. So someone's microphone is on. Kindly please like turn this off. So if you can see here, now we'll be seeing about the waveforms. Like you see, like this is our switching cycle TS here. This is the switching cycle. For certain amount of time DTS, where D varies from 0 to 1, we turn on the device. We turn on this device. And for this portion will be equal to then 1 minus DTS, then we turn off this device. As we know, like in the DTS interval, a positive voltage is applied across this inductor. So the current will rise in the inductor. So IL will rise to some point till the switch is on. As soon as we'll turn off this switch, now will be our DTS 1 minus DTS. So a negative voltage of minus V out is being impressed. Like if you can see, this is our convention. This is like voltage across this will be minus V out here. So since this is this will cause like the inductor current to fall. So it had risen to some point, and during this interval the current will decrease to the same point where from where it has risen. Like only then the volt second balance will be followed, because like if it hadn't be here to some, let us say this point, then in the next interval because the rise will be same, so our average would rise. That is what I was saying during the transient. So this is our input voltage across the inductor. That will be V in minus V out in the D interval, and minus V out in the 1 minus DTS interval. So here this current needs some path to flow, and we know like that will cause our diode to forward bias. It's not only about the voltage. Like if we have, and we need some path like that will flow. Like if you go through the diode, how it conducts, and you'll see like if you have some current, it needs some path, like it will cause this diode to forward bias, and because it needs some path to flow, and that it will flow through this diode. Now we'll see about the VD. Now we saw in the VD interval, like D interval, the voltage that has to be blocked by this diode is V in. So this is V in, and in 1 minus DTS interval it is 0. And similar to switch, in DTS interval the switch voltage will be 0, and 1 minus DTS it will be V in, like we discussed it. Now IS. So I switch, we saw that the switch voltage in the DTS interval will be equal to the IL. So this current will be the switch current in this DTS interval, that is this. So in 1 minus DTS interval, and this will be this switch current is 0, that is this switch current is 0. And if you can see, this switch current is the input current, that means this source current is discontinuous in the buck converter. Also you can see this ID here, you can see this ID conducts this IL, like you can see this IL, this is the current that is being conducting by this diode. So this ID will have this shape, like it will be 0 in the D interval, and 1 minus DTS interval, this will follow this thing. So now coming to the like CCM and DCM, now this is the important thing. So now we have seen different conduction mode. Like we have a continuous conduction mode, then we'll be having a boundary conduction, then we'll be having a DCM, like that is a discontinuous conduction mode. So when will this like CCM will happen? If you can see here, this is my, when will we say like we have a conductor in we have a converter in the CCM. So what will happen in CCM is our inductor current will be continuous. If you can see here, inductor current rises to some point, then it falls to some point, and then it falls to the same point in the steady state. Then only the volt second will be a balance, and then it rises again. If you can see, inductor current is like constant. And if you can see this inductor current, if you can see this dashed one, this will be some average component, and over this will be some, this is a ripple component, this delta IL, that will be from this peak to this peak, that will be delta IL. So IL will be component of average component IL and some ripple component, that will be delta IL here. So now what would happen, like if like we'll come to the numerical problem as well, only then you'll be able to understand what will be happen there. Like this is to help you with that, what is the CCM, like how will you look into the problem when different things are to be asked. You'll see in the problem solving, like we'll be going to, so what is happening there. So if you can see here, now what will happen if our load decreases, like we have a light load condition, that means our average current will someone is asking a question, so you can type or you can unmute and ask. Someone has raised the hand, so you can type the question and I'll see to it. Type the question if anyone has any question, or you can wait and we can discuss it later, like that this hampers the flow. So in the CCM, Now if we have a light load condition, that means our average current will decrease. Since if you can like see our IL decreases in the second condition to some point, like since we have a same ripple, this IL will decrease. As soon as it will decrease, like this point will be lower, and this will go on like decreasing. There will be a point when this point will hit this like zero line or the reference. That condition we call as the zero boundary condition. What happens, this is current starts from the zero to some point and comes back to the zero. Like this is our boundary case. Now we had a CCM where we had a continuous current. In the boundary case, we have the continuous current, but current starts from the zero and comes back to the zero. Now what will happen if current will IL will still decrease? If IL still decreases, then the starting point of the current might be negative. Then it will go to some value, then it shall decrease again. What does that mean? That means that if you can see this, there is some IL current. This current is positive. If the current is positive, it will flow in this direction in 1 minus d interval. So when it flows in this direction, it high frequency component will go through this and average will through this, and here we have a IL component, and this will followed by this diode and it will flow through this. When the current is positive, that means in this direction. Now if the current is negative, that means current has to flow in this direction. So Omkar has raised the hand. You can type the question and I'll see the question. So now if we have a negative current, like we know that diode cannot allow the current in this direction from cathode to anode. That current can flow from anode to cathode. So there is no path for the flow of the current. As such, the current will reach to some point and then it will decrease to some point, then we'll have a zero current. This means that our inductor current is not constant, and it is now discontinuous for some time. And here like these equations won't follow, and there are like different equations for this DCM part as well, and that is the beyond that has not been discussed in this course. I don't think that will be discussed here, but there are some other courses and you can see some if you want to like get an insight in the DCM. Like there is one book by like this power electronic converters by this fundamentals of power electronics. Just a minute. Sorry. I was saying, like, if anyone is interested in the DCM, that he can see some references. Like you can search discontinuous conduction mode in DC-DC converters, and there is a good book that is by Robert Erickson, Fundamentals of Power Electronics. You can see there, but this hasn't been discussed in here. Then our like equations, because like you see the conduction period changes now. Our you can see now it is conducting to this point only, and we have like a different intervals for the conduction, and then our we have to take into the consideration there as well. So coming then we can see here like in the buck converter analysis in CCM and DCM. So we have like we know in the DCM, if you can see here, like I said, we have some average component and some ripple component that will be equal to delta IL. If you can see, our current rises to some point and like comes back to the zero here. So if you can see, our average will be at the half of this. So if you can see at our boundary condition ILB, the average of the inductor current will be equal to delta IL by 2, and we know that delta IL we can get from different equations. Like we know L will be equal to LDI delta IL by delta T in VL is equal to VL will be equal to LDI by dt. So delta T will be equal to DTS in DTS interval. We know what is the voltage across the inductor in that interval. We know if we know the value of L, we can get that ILB. So substituting this into this, then ILB will be given by this equation. And if we like take into the consideration the 1 minus d interval, then the equation will be this. So here, so now coming to the like how can we choose the L, coming to the design part of it. Like if you can see in the buck converter design, choosing the L, so we know, like we have an equation, we know the voltage in different intervals for our VL in DTS and 1 minus DTS interval. So VL is given by L dl delta I by dt. So this we'll apply in DTS interval this thing. If we know V in, V out, we know the D for which our switch is turned on, and if we know the switching frequency, we can get, and if delta IL is specified, we can get the value of the L, and if our L is specified, then we can get the value of the delta IL here, given by these equations. And if we know, like usually in the questions, as we'll be discussing the problem, like there is some given, like the ripple will be some percentage of the output current, and we know, then we'll be knowing the value of the delta L, and only V in we know, D will be knowing, then Fs will be knowing, only the variable that will be there will be L, and then we will be able to like calculate this what I'll say is this the value of the L. So you'll see in the problem, and it will be much clearer to you. Similar to this, now coming to the how we'll be choosing the C. So we know, like the ripple component, we know that the average inductor current has some average component IL and some ripple component, that is delta IL. We know that the high frequency ripple will flow through the capacitor, and average component will flow through this load. So if we have this ripple component, that will be through the IS, so it will have an average of 0, and then only charge will be balanced. So you can see here, so we'll calculate what will be the charge stored in some interval here. So this the time interval that will be from this point to this point will be Ts by 2, and if you are able to like calculate what is the charge stored here, then we know Q is equal to CV by the formula. So we know the area under this triangle is equal to half of base into altitude. We know that thing. Then delta Q will be equal to 1 by 2. What is the base? That is Ts by 2, that is given here. We know the frequency, and what is this delta IL? We know that this amplitude like is delta IL by 2, because like whole is delta IL from this point to this point. So if we know this, that will be equal to CdV, and if we rearrange these things, and we know the delta IL in a certain interval like DTS, what will be that? We can substitute that thing in here, and we'll get this delta VC will be equal to this. If we know the ripple, then we can calculate the C. If we know the C value, then we can calculate the delta ripple. Already like we know how to calculate this L. So these are dependent on one another. When we know the value of the one thing, like we'll be able to like calculate the value of the other thing. The complete derivation of this equation is like has been taught in the course, and you can go through the transcripts, like then it would have taken much time here if I would have given in the detail. I think like you should have like see that thing during the lectures, course of lectures, or if anyone hasn't, like he can go to the Design of Power Electronics Converter by Shabrinath in the YouTube and go through the lectures and the transcripts. So there is another topology that has been discussed here. So any questions we'll be discussing at like the time is running out, like I shall complete this. Any whosoever will have questions, we shall have some time at the end and we can discuss the questions. Anyone, kindly note down your questions and we can have the discussion at the end. So I'll finish up with this, like then if I'll go into the questions then the main thing that the problem solving will be there. You have these questions and we can discuss these questions at the end. So now we have an H bridge here. H bridge also like a full bridge. So what we'll be having, we have like this is an inverter. We have some DC voltage source, then we have some like two legs. You can see leg A and leg B, and what we have the four switches here. Leg A consists of A plus and A minus, and similar is B, and we have load that is connected between the A and B point. So like there are 4 switches. So what is to be kept in the consideration is here that these 2 switches, no 2 switches in the same leg should be on at the same time. That you know why? Because like if any of the switch, if both of the switches in any of the leg, be it A or be it B, will be turned on at the same time, then the source will be short circuit and there will be a huge current, and that will damage our like devices. So then what are the different possibilities that we have to switch on these devices? So possible switching is like when we have TA plus, this A plus is turned on and TB minus is turned on. If you can see, like if these two are turned on, then what will happen, like what is the voltage that will get across A and B? If you can see, this is the path that will be traversed, and the voltage that will be across this load will be equal to VDC. And there is another, like we have like this B plus will be on and A minus will be on, and at that moment what will happen is, if you can see, this path will be traversed and V out will be equal to minus VDC during this, when TB plus and TA minus are turned on. And if like at the same time TA plus and TB plus will be turned on, you can see then this path will be there, the current will flow in this direction, and there will be a zero voltage across the loop. Similar is the case with TA minus and TB minus. If we have these 2 switches that will conduct, then there will be a zero voltage that will be impressed upon across this load. There is also one thing, if you can see, like if my current is like positive and my TA and TB is on, then my switches will conduct, like the current will flow in this direction. Everyone is able to follow sorry, this direction. And if my TA and TB are turned on, what will be the flow of the current? Then current will have an opposite direction here. So current will be opposite to this direction, I out, and if you see this, it will flow, since this is turned on, like it will flow through this diode, it will have the path through the diodes, and this current will have to find some path, and what will cause it forward bias this diode, and it will flow through this diode. We will see the analysis in different terms. Let us say one of this interval is this interval where TB plus and A minus are turned on. If you can see here, my V out, if you follow this path, V out will be equal to minus V in. If you can see, this negative point is connected to the positive terminal and positive is connected to the end point. So my V out will be equal to minus VDC, and you know that then the path, if my positive is current here, then IDC will be equal to minus I out. Now what I had been discussed earlier is, like if my current is positive, then what will happen? Current is positive, it will flow, if you can see, in this direction, follow the cursor, and that it will, since this is turned off, then it has to find some path here, that this switch cannot conduct in this, so we have an anti-parallel diode here that will be carry this current here. So when my current is positive in this interval, then DA minus and DB minus will conduct, DA minus and DB plus will conduct. And if my current is negative, that means current is in this direction, then the current will flow through the TA minus and come to here, and TB minus, and it will be opposite to this I out minus. Here you can see this if you apply the Kirchhoff's law here in this loop, you can see the voltage that is being blocked by this switch will be equal to VDC, like this DC blocking voltage, this. And if you can apply this same with this bigger outer loop, and you can see the voltage that is to be blocked by this switch is VDC. That means, like if you see the other interval, this voltage that will be blocked by these switches is VDC. Now coming to this another interval, similar will be the case when TA plus will be conducting and B minus, and you can draw the circuitry in those interval as well. If you can see here, now if my top 2 devices, or be it bottom 2 devices, are turned on simultaneously, then at that moment what will happen is current will circulate in this loop. That will my output voltage will be equal to 0 and input current, that IDC, will be equal to 0. And in the similar case, if I out is greater than 0, then if you can see, it is if positive, then current will flow in this direction and it will flow through the dB plus and TA plus. If my current is positive, if it is negative, then it will flow through dA plus and TB plus. And if you can see here, similar to this, like the voltage that is to be blocked by this non-conducting devices will be equal to VDC. Now coming to this was about like how it operates, that edge bridge. Now coming towards the modulations. Like we know there are like two modulation strategies for this edge bridge. First is like bipolar PWM. What does this bipolar mean? Bipolar, if mean like two poles. Like if you can see, I shall keep it here. Two poles like bipolar. If you can see, what happens is here, how we keep switching to these pulses, we have some carrier, like you know that if you can see that this gray shaded triangle, we call this a carrier, that is V carrier, and we have some reference and we have our logic in such a way, like if my Vref is greater than this carrier, then my TA plus and TB minus will turn on. If my carrier is greater than my reference, then TA minus and TB plus will turn on. What will happen at that time is, if you can see, when TA plus and TB minus are turned on, you will see that we will get a VDC voltage at the output. So Vout will be equal to plus VDC when TA plus and TB minus is turned on. And when TB plus and TA minus is turned on, we have like minus VDC across the load, that Vout will be equal to plus VDC and minus VDC. So since here you can see that the output voltage has the two polarities. For some instant it is positive plus VDC, and for some instant it is minus VDC. So that is why it's called bipolar PWM. Also, like if we have an inductor, if we have a resistive load here, then means that current will follow this output voltage. It will be like a straight here and straight here, like positive negative. But if we have an inductive load here, inductive won't allow certain change in the current. Then when positive voltage is impressed across this inductor, then current will rise to some point, and then after, when the negative voltage is impressed across this inductor, the current will start to fall, and it will fall to some point. Then after, when the switch is turned again on, then current will rise again. This will be the switching component of the current, and that will be some average component. We'll have an average component as well as some switching component. Now we'll look into the DC. As I told you, when TA plus and TB minus is turned on, IDC is positive, so it will follow this. DC current will have this positive voltage, will be positive, and it will follow the same as this. Now if my TB plus and TA minus are turned on, and in that sense we saw that if we follow like this positive current, my IDC will be equal to negative. So it will be of the, since it is the same current as the inductive current, load current, and it will have but the opposite polarity. Like my IDC current will be look like this. That is, my source current will have positive as well as the negative values. This was with regards to the bipolar. It's called the bipolar because we have the two polarities. Similar in us. Now coming to this, we'll see what is the average voltage across like this for this bipolar PWM. Like in the buck converter, we applied, like we know, if we assume this, when it is turning on in one switching interval like this, it is turning on for some DTS time. We have a Vout average of the V output voltage will be equal to VDC into DTS, and minus VDC when we are having the other leg diagonal switches of the other leg turned on, then the minus VDC voltage is impressed across the load. So it will be minus VDC into 1 minus D into TS, and the average will be divided by TS. So if we'll solve this, the average of the output voltage that we'll be getting is Vout will be equal to VDC into 2D minus 1 for this case, bipolar modulation. And if you can see now, if you want to know the D, if you can see, if you rearrange this thing, then D will be equal to V out by twice VDC plus 1 by 2. If you can see here, we have a DC shift of 1 by 2, DC shift of a half, and we have D will be equal to V out, average of the output voltage divided by twice VDC. This here, if you can see, are like this reference is a constant, and we'll be having the same width for each and every switching cycle. Now if we want to have a sinusoidal voltage, now we have an inverter operation, as I told you, these are used as an inverter. Now if we want to have a sinusoidal voltage at the output to drive the motors and etc., so what will we do? We'll have a reference that will be sinusoidal in function. So our output will be equal, we want our output as the sinusoidal, so our D will vary in such a way so that our, we know it will be equal to, now our output will be this is the since we want our output to be sinusoidal, and our reference will be in such a way, and since this D is our reference and this will be equal to Vref, that will be equal to V out into sine omega t divided by twice VDC. This is the amplitude and this is the sine, because we want a sinusoidal voltage. You might have read about the sine PWM. This is that what we are talking about. And if you can see here, this will be clearer to you here. Now we have a carrier here. If you can see these triangles, these are the carrier, and we have a modulating signal, that is this Vref. This is the Vref that we want at the output. So if you can see, since we want this V out at the output, we have this Vref is what Satish has raised a hand. Like, you can type the question and I shall ask if you have any confusion, if you are not able to follow, or you can unmute yourself and ask. Satish. Okay. So this is the output voltage that we want at the output, and that is the reference that we will give. So Vref equal to V sine omega t, that is what we want at the output. So if you can see here, now our reference is varying. So for this amount of time, some switches will be turned on, then it will be turned off. And if you can see here, now my switch is being turned on for more time and my turned off for smaller time. If you can see, the pulse width of these the width of these pulses is varying in a sinusoidal function. In a sinusoidal way, we'll be having a fundamental, and over this we'll be having some other harmonics as well. And if we apply a filter at the output, and that will filter out only the fundamental, we'll be getting a pure sinusoidal wave. So we know that now we wanted a reference of a sinusoid at the output. That is why we have this V out sine omega t. And we introduce a modulating index that we see that this V out cap, that is the voltage that we want at the output, and divided by VDC. This is called as MA. So if I put MA here, that will be equal to MA sine. So I'll be coming to the this is like the two slides here, and I'll come to the solving part. Then this is given by the MA, and as you have read in the detail, I won't go into much of the detail here. So now if you can come here, now as I told you, I wanted the car voltage that should be sinusoidal here. That is why we have our reference that will be sinusoid in a way. So if you can see, our widths will vary in this fashion, and it will follow, the reference will follow in this way, the voltage. We'll be having a fundamental there underneath these switching and some other harmonics as well. So now if we see the current, so now my current, since this is the positive voltage that is being impressed, then my current will rise, and then my current will fall. And since now my turn on time is more, my current will rise for more amount of time. This turn off time is less. My current will also follow this sinusoidal fashion. And if you can see, both are sinusoidal fashion, where we have an average component that is being given by this dotted line, and over this is a switching component, switching frequency component. So now we have our V out, we want is V out sinusoidal, and I out as the sinusoidal. If we like, if we'll like have a power. We know that as we are dealing with this what am I saying, what I should say is like ideal things, then input power should be equal to output power. So VDC into IDC should be equal to V out into I out. If we multiply these two things, we'll be getting a DC power that is being given by V out I out by 2 VDC and cos phi. And if you can see in the single phase system, what we'll get in, we'll be getting another component that is a pulsating power that will be pulsate at double 2 omega frequency. If you have a 50 hertz, this will be at like 100 hertz. That this is inherent to this single phase system, and this thing we don't observe in the 3-phase system. And if we have the 3 voltages in the 3-phase system, and if you will multiply them, and you will find a constant power like 3 V phase I phase into some power factor cos phi. And IDC will be same as the I out, and it will be positive. As I told you, it will be positive when the switches are turned on, and negative when the switches are turned off. So it will follow this shape, and you can see over this there will be a 2 omega ripple. So this was about the unipolar. Now coming to the bipolar. And this was about the bipolar. Now coming to the unipolar. So in the unipolar, what is different? Like circuitry is different, but we have instead of a single reference, we have 2 references here. We have a separate reference for A leg and separate reference for the B leg, and we have the same carrier. And if we have A ref at some point, and VB ref will be opposite to that, 1 minus VB ref will be equal to 1 minus VA ref. So now if you can follow each leg, if we will follow, so following the same thing, when my reference is greater, this will be turned on. And if you can see, when my reference is greater, this TA will be turned on, and with respect to this VA with respect to N, will be getting a VDC voltage. And when this is lower, we'll be getting a 0 voltage, because we are only talking about this leg. When this is turned on, we get a with respect to this point, N point, we'll be getting a VDC and 0 when this is turned on. And similar to this B, when this TB is positive, and we'll be getting a VDS. When this is less than the carrier, we'll be getting 0 voltage with respect to this N point. Now if we want output voltage VAB, that will be equal to VAN minus VBN. If you will subtract VAN minus VBN, we'll be getting the VDC. And if you can see here, this will be equal to 0, and this will be plus VDC here, and so on. If you can see here, the voltage, it is in the unipolar direction. It varies between 0 and VDC, and we have some average and some average component here V out. And similar to this, we have an output current, like current will increase when the voltage is turned on, and it will decrease. And if you can see here, IDC IDC will have a path like when this is out is turned on, you will see here these switches that will be turned on, IDC will be positive, and in this 0 interval there will be no path, because like either the top 2 devices or bottom 2 devices will be turned on in this point. Like if you will see, because here TA minus, and if you can see here, TA minus and TB minus are turned on, bottom 2 devices, and there will be a 0 current, that IDC. So IDC will have a positive and 0 value. So the source current will follow the inductor current, load current. When this we have the positive voltage, and it will be 0 in the other interval. So here what we saw is compared to the unipolar. So we'll have a comparison. Similar to this H bridge, we have as we saw in the unipolar, we have a VA ref that will be called V out by 2 VDC plus 1 by 2. Similar will be VB ref, and if you follow similar analysis. And same will be the case with here. If you can see, if you want a sinusoidal PWM, that was for the constant. Now if you want a sinusoidal voltages at the output, we'll have 2 references that will be phase that will have a 180-degree phase apart from one another, VA ref and VB ref. And you can see are like VAN voltages will vary in the width of the pulses will vary in width of the voltage will vary in such a way. We'll be having a fundamental will be having a positive average when my reference is positive, and when my reference goes to negative, we'll be having a negative average. Similar with the B. And if we then we want an output, what for the output, similar to the constant case, we want VAN minus VBN. And if you can see, we'll be getting a positive voltage in the positive half cycle of, and then negative voltage in the negative half cycle. And here you can see the voltage varies either from positive to 0 to positive or 0 to negative. That means our voltage is a unipolar. That is why this is called a unipolar uh, modulation. And the analysis follow the similar in a similar way as like the bipolar modulation. And compared to this here, if you can see, like as I told you, like when the voltage will be positive, like the current will rise and then it will fall in the 1 minus interval. If you can see, compared to the unipolar, the frequency of the higher frequency will be the higher frequency component in the output voltage will be the twice of the switching frequency. If we switch the unipolar and the bipolar, if we switch the devices at the same frequency in the unipolar and the bipolar, in the unipolar we'll be getting the twice switching frequency compared to the bipolar thing. That is evident here if you can follow this thing here. And similar to this, the output will have the DC component and some 2 omega component. So if we compare this unipolar with bipolar, unipolar with a bipolar, like we have the transition, as we know. If you can see the first point, we have a transition from like a VDC to minus VDC. There is a very much jump from like minus VDC to VDC, and this is not good for the insulation or EMI purposes. What we want is as minimum of a jump as possible. So someone says mic is on, kindly please turn off. So as I told earlier, like if we have unipolar and bipolar, in the bipolar we have a switching frequency of fs in the load, and if you can see in the unipolar we'll be having the switching frequency at 2 fs here. That is quite evident as we saw here how it is followed here. And also what we saw is here in the DC current supplied by the source, like we had the positive as well as the negative voltage. Like the ripple current ripple was high from the source like DC in the bipolar, and in the unipolar we had only from 0 to some peak, some positive voltage, and therefore like current ripple is less in case of a unipolar as well. Like this was a briefly we had discussed. Like I think it got dragged a bit. Now we'll be coming to the problem solving session. I think like we'll have a like break for 2 minutes, and we shall come back and discuss the problem. In the meanwhile, like you can like take a look at this problem. Like it is 4:20. Like at 4:22 we should join back, and we shall discuss. Now this problem will be about the boost converter. Now how will be designed, the specifications are given. Similar assignment has been given to you, but that is buck boost type, and you will see following the similar way. In the similar way you will be able to like solve that question as well. So we shall like continue this thing after the 2 minutes. Hello, am I audible? Everyone is there? Hello.
Yes, sir.
Yes, sir. Yes, sir. Audible.
Yes, sir, audible. So now coming to the problem solving. So this is the problem. This is the problem that we'll be discussing here. So we just saw this the analysis of the buck converter. How we saw the analysis of the buck converter, like how we'll design different parameters and all. Now we'll be seeing about the boost converter, how it is done. So this problem, like we shall be this question is being so there are around like 4,000 students that have enrolled in this course. So all the three all the three problem solving session will have the same material. Like if someone was not able to join yesterday, he or she will be able to join today. So there shouldn't be different like material that will be in a different problem solving session. So for the uniformity, like the problem solving will be the same, and I don't think it will matter a lot. The only thing is you need to get the understanding how to solve the question. So if you are able to get that, grasp that thing, then you will be able to solve any question. I hope like you are able to follow. So we have a question that we'll be discussing is like there is a boost converter that we want to design. So as we know, the boost, the output voltage will be like the higher than the input voltage. So input voltage is given, like it is around 30 volts, and output voltage is given like it should be around 75 volts. So we have like peak output power should be equal to like 300 watt. And see, that is what I was telling, like here the ripple is like given what should be the ripple in the output voltage. Here it is the maximum ripple in the output voltage should be 0.1% of the V out. We have given V out is 75 volts, and if the ripple that should be in the output voltage, it should be 0.1% of this output voltage. Then the boost converter should remain in the CCM for the load change of 150 watt to 300 watt. Like I told you, if we what we saw in the buck converter, same would happen in with any other DC-DC topology, be it boost or buck boost converter. If we have a light load condition, like our power level decreases, our I average will decrease. So that will cause our converter may go into the DCM mode. Like what we saw, there will be first a boundary condition where my inductor current will start from 0 and come back to 0, and after that if my if my load further decreases then it will go into the discontinuous conduction mode. So here what is being done, like we have to design the converter in such way that between 150 watt and 300 watt my converter should operate in the CCM mode. So we'll see how we'll do this. Also, the maximum ripple allowed in the inductor current is limited or to like 15% of the load current, that is I out. That what is also given is the ripple in the the ripple in the inductor current is 15% of the out, like the load current. We'll see how we calculate the load current, and then the ripple will be 15% of that. And also it is given that the switching frequency is 50 kilohertz. So if you can see, this is the boost converter example. In the buck we had a switch where we have an inductor, then here at the diode we had a switch, and here we had a diode. So the circuit of this boost converter is where we have a V input and we have a V output. So VL is the voltage across the inductor, VD diode, and this is like the switch. So here also we'll be going through like different intervals. In the D interval when my switch is turned on, and 1 minus D interval when my switch is turned off. So we'll look into the different like intervals here. So if you can see, this is my boost converter here. Now coming to the DTS interval, similar to this boost buck converter, in the DTS interval what will we have is my switch will be turned on, like this switch. Follow this cursor. My switch will turn on. My switch will turn on, and also we know for the boost converter V out is greater than V in. So whatever the voltage that will be here, that will be lower than this output voltage. That will cause the reverse biases of this diode. So my diode will be reverse biased. So in the DTS interval, the voltage across the inductor will be equal to VL, which will given by, we know VL is L di by dt, and that will be equal to, if we apply the Kirchhoff's voltage law here in this loop, VL will be equal to V in DTS interval. Also, if you can see, we have the capacitor current and the output current. If you can see, my capacitor current will be equal to my I out. If you can see IC, both of them are coming out of this node, and they should be equal to 0. And if you like rearrange it, IC will be equal to minus I out. That my I out will flow in this direction. It will be equal to IC is equal to, we know that C dV by dt is the current through the capacitor, and that will be equal to minus I out. Since my switch is turned on here, so the voltage across the switch will be equal to 0, and my like inductor current IL here will be equal to IN. My I switch current will be equal to IL current. The current that will flow through the inductor is the IL current. Since like the positive voltage is applied across this inductor, what it will cause? It will cause like the current to rise, and we'll see the waveforms of this topology. And same with this, since if you can see this VD, if we apply this Kirchhoff's law loop in this that VD will be equal to V out here, that this diode has to block this V out voltage, and ID is 0 here because diode is not conducting. Now coming to the 1 minus D interval. So in 1 minus D interval, what will happen? My switch is turned off when my screen is not visible. Just a minute. Am I audible?
Yes, sir.
Screen is visible?
Yes.
So I think there is some problem with that student only. If my screen is visible now?
Yes,
Everyone?
sir.
Okay. So there might be problem with that person if like they can restart their Google Meet. So in 1 minus D interval, what will happen is like this switch is turned off. When this switch is turned off, then this diode voltage will be diode will be forward biased, because like this inductor this current has to flow, and this will cause this diode to forward bias, and my VL will be here will be equal to V in minus V out. Will be having some voltage at the output, and it will be equal to VL will be equal to V in minus V out. You will see, it will be much clearer in the waveform in the next slide. my IC here will be equal to, if you can see, if we apply this Kirchhoff's law here at this node, it will be equal to ID will be equal to IC plus I out, and my ID will be equal to IL here. So if you can rearrange this thing, we have IC will be equal to IL minus IC will be equal to IL minus I out. Since here the diode is conducting, so the voltage across the diode will be equal to 0, and my switch, if you can apply this voltage loop in this here, the voltage that is to be blocked by this switch is the output voltage here, if you can see here and here. So the voltage that my switch needs to block is V out. My I switch will be equal to 0 at this moment, because like the switch is not conducting at this moment. My diode will conduct the inductor current here. So in the similar fashion to the buck converter, we will apply the volt second balance here in the switching interval. So in DTS interval will be equal to V in into D. In 1 minus DTS will be equal to V in minus V out. 1 minus D equal to 0. So if you solve this thing, we'll get V out will be equal to V in divided by 1 minus D. Since D always varies from 0 to 1, so this is the this 1 minus D will be always less than 1, and that will cause like V out will be always greater than V in, if you can look into this. Also, if we do the charge balance for this capacitor, so IC will be equal to minus I out in the D interval, and IL minus I out into 1 minus D interval. So if we'll solve this thing, IL will be equal to I out divided by 1 minus D. So I out, we know that will be equal to V out divided by R. So in this way, like we'll get the two equations, like V out will be equal to V in divided by 1 minus D, and IL will be equal to I out divided by 1 minus D. So coming to this the waveform. So as we know, like we have a TS interval. For the DTS, my switch is turned on. When my switch is turned on, if you can see in this DTS interval, there is a positive voltage that is impressed across this inductor. So my current will rise to some point. So when my current rises to some point, after that my this switch is turned off by some logic, and when this switch is turned off in 1 minus DTS interval, what is the voltage that is being impressed across this VL? That will be equal to V in minus V out. V in minus V out. As we know, V out is greater than V in. That means this voltage will be negative. So when this is negative, that this will cause this current to fall, and current will fall to the same point from where it has started, because this is in the steady state. Otherwise, because average is constant, if it hadn't followed this thing, then my average would rise after every switching cycle. Because it is in the steady state, my average is constant. So now coming to the I switch. So we know that the switch is conducting in the DTS interval. When it is conducting in the DTS interval, so the my switch current is same as that IL. So this is my IL, this will be my switch current in the DTS interval, and in 1 minus DTS interval it is 0. If you can see, that is here, and you can see here the switch voltage that is being given by the gray color. You can see the switch voltage is 0 when my switch is conducting, and after that it is V out. VSW will be equal to V out in the 1 minus D interval. Now coming to the diode. In the D interval, we have that diode is not conducting, so my diode current will be equal to 0, and the voltage that is to be blocked by the diode will be equal to V out. And in 1 minus D interval, the diode has to carry the current IL minus I out. This will be equal to VL, IL current that will flow through the diode. So it will have the same shape as this inductor current, because it is the same current that will flow through the diode. So my diode current will be equal to the IL, follow the same shape here. If you can see the IL, this is my ID here, it will have some average component that will flow through the load, and this ripple component will flow through this capacitor. Then if you can see the capacitor current, that will be IL minus I out, that this I out will be the average component. When we subtract it from there, then this ID will shift a little, so it will be equal to minus V I out. in the D interval, and if you can see, and it will follow this shape in this 1 minus D interval. So voltage across the capacitor, we know that if we know IC, if we integrate that thing, that will be getting the VC. So VC will have this shape. We know it is minus V I out, so my voltage will fall in the D interval, and in this 1 minus D interval, so it is feeding this current, and my voltage will rise in this DTS interval, and this is my delta V. So this is about the waveforms. Now we discussed. Now the question is, this was about the converter, how we operate it. Now the first question is, the voltage rating of X component should be above. So we have to get the voltage rating. If we want to design this converter, what is the voltage rating of the certain component? Now the first is the MOSFET, second is the diode, and third is the capacitor. So if you can see, like we saw, what is the maximum voltage that the MOSFET has to, like, I think now this should be clear to you. In the 1 minus D interval, the switch has to block the output voltage. So my MOSFET should the rating of the component of my MOSFET should be above output voltage, that is 75 volt. And for the diode, you can see in the DTS interval, the voltage that the diode has to block is the output voltage. So for the diode, the voltage rating of the diode should be above like output voltage. So that is the answer to the question number 1 and question number 2. Capacitor will also have the output voltage, but it is being given in the I hope this is clear to you. It is clear. Is it clear to everyone, like why this MOSFET should be above 75 volt and diode should be above the 75? Clear to everyone? Anybody? Oh, okay, fine. So this is the way, in a similar fashion, you can solve your assignment. Why not V in? You can see, if you can see this, my switch in this interval, what is this voltage across this diode? Positive terminal is connected to this, and this point is converted to this point. There is nothing in between. Whatever will be the output voltage, that will be across this diode. Similarly, in a fashion, in this 1 minus GTS interval, if we take the V in, if we apply this here, the voltage law, if you can see, we have an inductor. There will be some voltage drop across this inductor, and the voltage of the switch, there will be some voltage across this inductor, and it won't be same as that V in. Now if we apply this loop in this, this voltage is equal to this, and here it is this. It's in parallel, if you can see. So the voltage of this switch will be exactly of that of the output. I hope this is clear. Is this clear? MOSFET 1. See, if you can see 1 minus DTS interval, if we apply the voltage loop here, then you should be, then we have a V in, then we plus VL plus V MOSFET should be equal to 0. Then we should be knowing VL as well. If you are able to calculate this, then you can get this. A simpler way is, we can apply this voltage loop in this, where we have V MOSFET will be equal to this V out, because there is nothing else in this loop. So you have to see what is easier. Here in the input loop, there is an inductor, and you have to then calculate the voltage across this inductor as well. I hope this is clear to everyone. So this is 75 and 75. Now coming to the capacitor. Now it was given that capacitor ripple is around 0.1% of the V out. So we have the V out. So peak capacitor voltage will be equal to V out. Then we have the ripple, and ripple will have average is 75. Then we have a delta V, and the ripple will be overlapping this average value. It will be delta VC by 2 above and delta VC2 by below. So peak capacitor current will be equal to 75 into plus 0.1% of 75 divided by 2. That will come around to be 75.035 volt, and if we round off this, then it will be equal to 75.04 volts. I hope this is clear. Now there is, based on the limit on the current ripple, the current rating of the X should be above. So now we saw the voltage. Now we have to see the current limit. What should be the current limit? First is the MOSFET, diode and inductor. So see, if you can see here, what is the current that is flowing through the MOSFET? The current that is flowing through the MOSFET is the IL in the DTS interval. So this is the current that is flowing through the MOSFET. Correct? So there will be some average component, and over that will be delta IL by 2. That is the peak current that will flow through the MOSFET. So if we are able to, what slide? This slide? This is the based on the limit on the current ripple. The current this. So I'll come to this. I am discussing this now. So now we have to see the current reading of this. So we'll see about the, we have to calculate MOSFET, diode and inductor. If you can see, through the inductor the current is IL like this. This will have an average component as well as the ripple component. So IL is the average. What is the peak value it will go? It will be IL plus delta IL by 2. That will flow through this switch MOSFET. Now in the 1 minus DTS interval, diode current will start from this peak point. So this is the maximum current that will flow through the diode. So it will be the same current that we'll be getting in the DTS interval that will flow through the switch. And we know that the diode current is equal to the IL inductor current in the 1 minus DTS interval. And we know that this is the IL and it is the maximum value that will flow through the inductor. So coming to the question, we have to see the current limit on the current ripple, the current rating of these components. So we saw through all these components, the peak current that will flow will be equal to IL peak, that will be average of the inductor current plus delta IL by 2, that will be the ripple that will come to the peak. So we know we had derived the equation in the previous slide that IL will be equal to I out divided 1 minus D. So I out will be equal to V out by R, and this is equal to 15% of this I out. No, I out will be getting, we have power rating. So we have a power rating of 315 given. Power rating and voltage is given, and we can get this I out. We know that V in into I in equal to V out into I out. From that we can get this I out. Also we have D. We know D is equal to V out. We know D, we have the V in is given, V out is given. We know that V out is equal to V in divided by 1 minus D. From that we can get the D, and if you will be getting the from power and the current, then you can calculate the D, and when you put these values here, then this will come out to be 10, and this is 15% of this I out. If you will calculate, that will come around to be this 0.6, and that will be divided by 2, that will be equal to 0.3. So IL peak will be equal to 10 plus 0.3, that will be equal to 10.3. So we have the output power, we have the output voltage, we get the output current, and you can calculate the D as well. We have given the input voltage, output voltages that we have, and you have the equations for that. You can calculate the D and you will get this value. So the peak current that will flow through all these components will be 10.3 amps. I hope this is clear. Now coming to the other part of this question, the value of the L critical is. So we saw the L critical is, we have to see, note is given that you need to consider the entire load range given for the CCM. So we had given that load range should vary from 150 to 300 watt for the CCM. This is for this. Earlier the power was this. Now we are coming to this point. Now my load is varying from 150 watt to 300 watt. When my load is varying, we know for the light load condition the average current will decrease. When my average current will decrease, now there will be a boundary condition. What we want is at our 150 watt, my converter should still be in the CCM. So what I will do, I will calculate the I out at the minimum power. So at minimum power, we know it is 150. We'll be getting the I out at that moment. That will be equal to 150 divided by V out. That will be my I out. That is my I average. That is this. So this will be equal to, we know my average in the boundary condition will be equal to delta IL by 2. Delta IL by 2, because this point to this point is delta IL, and that will be equal to 1 minus out 1 minus D, because we know IL be equal to I out divided by 1 minus D. That will be equal to delta IL by 2. So if we, from this we can calculate the delta IL, that will be equal to twice I out 1 minus D. So we know the I out, D will be the same, so which we had calculated previously. We can calculate the delta IL. When we get the value of the delta IL, then we can have, we know the voltage in the DTS interval across the inductor is V in. So VL will be equal to L delta IL by delta T. From this delta IL we know V in will be getting, delta IL will be equal to V in for the DTS interval into DTS divided by L. So L critical will be equal to, we know the delta L that we had calculated here, that will be equal to V in into D divided by twice IB out. Like substituting this and this here from these two equations, we will get L critical here. We know the V in, we know the D that we had already calculated previously. Then we have the I out. We know switching frequency, we know that L critical will come out to be 36 microhenry. So if we have a inductance of 36 microhenry, then our converter will operate in the critical condition mode. So if my inductance is higher than the 36 at 150, that is, this is at 150 watt power. So if my inductor is higher than this 36 microhenry, then my converter will certainly operate in the CCM. But if my inductor is lesser than this 36 microhenry, then at 150 power my converter can go into the DCM. Then L critical microhenry is already unit is given, you have to only write the 36 here. So coming to the other question, now what it is asking is the value of the L ripple is dash microhenry. So to have the same ripple that is already given here in the question, for the certain ripple 15% of this load current, we need to see what is my inductor. We have to now keep the ripple constant. So coming to the answer of this question, like how we can do this is, we know this for DTS interval, VL will be equal to L delta IL by delta T, and VL is equal to V in. So L ripple will be equal to V in into D delta IL into Fs. Sure, got it? So now we will see that we will see the minimum current that is flow, that out minimum will be equal to my minimum out. We have a variation of the load from 300 to 150. We will see where at what load, at the extreme positions, where my current is minimum, and it comes out to be wherever my current is minimum at that moment. We will see now my load is varying from 150 watt to 300 watt. Now we will see the two extreme conditions at the 300 watt and 150 watt. Now we will see where my ripple is more, and we have to limit that ripple to the, we'll calculate the ripple at both the extreme points, and what we want is what will be the value of the inductor in both the cases, and wherever the inductor value will be higher, we will choose the higher value. Why? Because if we let us say at one extreme end my inductor value is coming out to be, let us say, 10 micro, and other extreme end my inductor value is coming out to be, let us say, 15 micro. Now if I choose for the same ripple, now if I choose 10 micro, then at the other point, at the other extreme boundary condition, I won't be having the same ripple limit. But if I choose the larger of the value, then my ripple will be always be under that 15%, because it will it will be under the 15, it will be under the 15% in both the cases. At one extreme end where we have chosen the inductor value, where we have chosen the higher inductor value, my ripple will certainly be around 15%. Where lower inductor value was needed, but we have a higher inductor value, certainly my ripple will be below that, like 15 below that 15%. So that is, it comes out to be, we'll have, when we calculate, it will be wherever my I out is minimum, this will be equal to 15% of I minimum delta IL, that will be equal to 0.3 ampere, and my L ripple, substituting this here in the equation, we know V in will be knowing, D and Fs we know, and if we calculate, L ripple will come out to be 1.2 millihenry. But we want this answer into the microhenry, so that will be equal to around approximately equal to 1200 microhenry. So 1200 microhenry is the answer. So now coming to the last question, like this is based on the above calculation, which among the following value of the L you should choose for the design. So now we did the different calculations. So what do you think, like to have the certain ripple, what should be the value, what should be the value of the inductor? I think now this should be clearer to you. Anybody can guess what should be the value of the inductor? Then he can write out, he or she can write in the chat. Yeah, like one people is asked, like we saw, like to have the inductor current in the ripple current under this 15%, we certainly want to have the inductor value above this 1200 micro, because if it will be below this 1200, then my ripple will increase. So my inductor value, in order to be below this 15%, my inductor value should be greater than this 1200 microhenry. So the option that is correct is 1275 micro. That is the correct answer. And that was this about this how we design the boost converter. And in a similar fashion, you will find your assignment for the buck boost. What you will do is, like, you will analyze that circuit for the D interval, 1 minus DTT interval, and see like which of the components are conducting in D interval and which of them are conducting in the 1 minus DTS interval, and see what is the current that is flowing through that component in that interval, and subsequently in other interval as well, and what are the voltages that are being blocked by these components in different intervals, and you will be able to answer all the questions. Like we are not allowed to like discuss about the buck boost, but once you will submit your assignments, then we can discuss that buck boost as well. But if you are able to understand how we did this for the buck boost converter, you should be able to do the buck boost as well. And that was it for today. If anybody have any questions, and now we can discuss. Anybody having the question, then she can ask. Any questions? If anybody has questions, someone had like the question earlier, like how this is like getting forward biased. Diode is will get forward biased here. So what will happen is, if you can see here, when as soon as this switch is turned off, this is the convention how we have written it. But now what will happen is, this inductor will act as the source, so the current should flow in the same direction, but this polarity will be reversed. So this now will be the because if you can see the source, the current will flow from negative to positive. So this will be now negative, this will be the positive, and current will flow in the same direction, which will cause this diode to get forward biased. I hope this is clear. Is it clear with everyone? If any other questions, like, you can ask. Yes. Any other questions? So if there are not any other questions, then similarly you can see for the boost how it is getting forward biased and all. So I think if there are not any other questions, then we can like close today's meeting. Thank you everyone for joining, and we shall meet on next Sunday from 3 to 5. Thank you. Thank you everyone.